Please have a look on these different supplementary cementitious material used in this experimental program with these following indicators: D50, yellow index, and density. We use D50 to evaluate the D50, we use the Malvern granulometry laser. For the yellow index, we use a data color measuring system as we do for PET application to evaluate the brightness of the product. Here you can see at a glance the wide surface area of the calcined clay covered by this, you see the wide area of the calcined clay evaluated in these studies with a D50 ranging from 1.3 to 8 micron, a yellow index from 8.6 to 49.9, and a density from 2.2 to 2.6. That is to say, since the beginning, we can see that this variation, this area, shows the variation of the raw material and also the plant process parameters. Perfect. The first model formulation is a Pascal consistency mortar. You know this one, you use it for cement application. And the strategy is really to use this calcined clays in substitution of the cement part from 10 to 50%, weight by weight. The mass, the solid content cement plus calcined clay is constant, and we will keep the same flow behavior with the adjustment of water. For the flow behavior, we will use this Hagerman cone, and the strategy is to target 200 millimeters with the jointing table 16 times. After, we will be able to use a cabinet chamber as in CIN mortar standard, the storage and water, and the compressive strength. This is the strategy of this first model formulation. Here you have an overview of the main results. We have different calcined clays, and we can see that depending on the calcined clay, the water requirement of each of them is significantly different. M2 and M3 products, for example, I'm very careful with this tool, okay, with a finer D50 require more water. On the right, the figure shows on the axis the proportion of calcined clay, on the vertical axis the compressive strength. And we can see that depending on the calcined clays, I need to move, sorry, I'm just trying to find the doors in the beginning. And you can see that depending on the calcined clay, we have a different contribution to the compressive strength. M2 product, for example, this one, with a smaller D50, require more water, but has a significant contribution to the compressive strength in a substitution rate, achieving 45%. That is to say, this combination requires more water, we have a higher relative yield, and that is to say, a lower cement concentration. We can also observe that these two calcined clays require less water, but have also a positive contribution to the strength. This shows the diversity of the calcined clay and the fact that all of them have a different water requirement. This is the first step, and we will complete this view after with the compatibility with superplasticizer. Sorry. If you have any question, you can remember the slide number here. Okay? This is the first part. The second model formulation, of course, when I speak about this point, just to remember, this is exactly more or less what we do with the activity index. This is just an extension of the activity index, but we have here the advantage of the variation of the proportion of the mineral addition and the first information on the water sensibility of these mineral additions. The second model formulation is, again, a Pascal consistency, and here the strategy is to evaluate the contribution and the performance of an ultra-fine ground calcium carbonate of high purity. So what we will do, we decide in this matrix to We start with a CIN mortar, water to cement ratio at 0.5. And we will reduce the cement concentration, keeping constant water, to vary the water to cement ratio. That is to say, the control will not be 1 point, but 4 points. And for each water to cement ratio, we will add the ultra-fine ground calcium carbonate to optimize the performance. And we will be able to evaluate the performance. This graphic on the right is interesting because we can see here, at the end of the day, the effect of the water concentration, but we see also the effect of the addition of the ultrafine ground calcium carbonate, because we will increase the total powder content. That is to say, we will play on the paste thickness of the system and also on the water film thickness of the system. Mon Dieu. Allez. Perfect. We have here, at a glance, the summary of the main results. You remember what we have seen just before for the calcined clay, and we observe here on the graphic, on the left, here the different water to cement ratio. And we can see that for all mortars of this matrix, with or without ultrafine ground calcium carbonate, we don't need to add water. And this is a positive information because here we are really enhancing the packing of the system. And I use this figure to give you also another point. When we have added this ultrafine ground calcium carbonate in the system, it was not in substitution of cement. The strategy is not here when we use a so high fineness of calcium carbonate with a high purity. The strategy is to optimize the binder compacity. So we use the ultrafine ground calcium carbonate in addition to the cement to optimize the packing and to provide some site of nucleation. The strategy is here. The mechanism is well known, but this is an existing product. On the right, you can see here the different water to cement ratio, and on the vertical axis, the strength at 1 day. 1 day, why? Because early age, we will see after, of course, 28 days, but the main added value of an ultrafine ground calcium carbonate is the added value of 1 day. And you can see that for all water to cement ratio, the positive contribution of the addition of the ultrafine calcium carbonate in addition to the cement. You have here, for this cement, the clear contribution of this ultrafine calcium carbonate, and this calcium carbonate in this model formulation has a surface area of 8 square meters per gram. And you remember the keys of segmentation at the beginning. Such a calcium carbonate has a calcium carbonate content at 98%, a methylene blue value of 2.6 grams per kilogram, and a surface area BET of 8 square meters per gram. It is a chalk-based calcium carbonate. That's why this mechanism is not rocket science, but to do that, we need a very pure calcium carbonate, and we need to reach this high level of fineness. It's more than limestone, definitely. Another comment, you see the curve of the control. This information is interesting. We will see after some example with CM1 and CM3. We have here a first information about the water sensibility of the binder, of the cement in this case. That is to say, we can use this model formulation to evaluate the performance of a cement alone, a combination of two cement, or a cement with one or different mineral additions. And we will not only consider the compressive strength, but we will be able also to consider the water sensibility of the combination. The next step here is this information at 1 and 28 days. If we want to evaluate and to feel and to measure, because the question is to evaluate, to have some data, the influence of the water concentration or water to cement ratio, the edge, and also the concentration of this ultrafine calcium carbonate, we can, for example, compare the strengths at 1 day and 28 days. We know, all of us, that calcium carbonate has no podogenic activity. Of course, a K-value at 0.25 in France, but this is a physical effect. That is to say, again, you understand why the strategy was to add this calcium carbonate in addition to the cement to show that. Because if we use it in substitution, forget, we decrease the water to cement ratio, and we increase the water to cement ratio, and as a consequence, you decrease the strength. So this model formulation, again, I repeat because this is important, we use it with our customer. We are able to evaluate the new cement they use, or we can evaluate the combinations they want to develop, CM1 plus slag or CM1 plus calcined clay. It is a benchmarking tool, but with a good organization. To give you more information, what we did in this collaboration, we did that with a cement producer, and we will here compare two different cement coming from the same plant, that you say we have the same clinker. In this case, it is a CM1. Mon Dieu. Ben non, Pascal. Sorry. It is a CM1. Perfect. And the blend surface area is 490 square meter per kilogram. And you can see that the clinker content is 99%. Again, we add this calcium carbonate in addition to the different water to cement ratios, and we can see here the contribution of this ultrafine ground calcium carbonate to the strength. You can, with this figure, you can see and understand why we sell such a product in ultra-high performance concrete or 3D printing. This is a mechanism. The next example is, alors, you see here, just for the remark, you see here the variation of the compressive strength at 1 day. We change the cement, and we are in this area. The question is, can I activate my slag cement with the use of an ultrafine calcium carbonate? Other question, can I use the calcium carbonate of ultra high fineness to wake up my binder in winter time? That can be a question. That's why, for example, such ultrafine ground calcium carbonate are used in tile adhesive as a substitute of calcium formiate. The point is, again, the same mechanism is very simple because we have an orthogonal matrix, the variation of the different water to cement ratio. This is we just represent here the proportion of cement. This is the slope of the control. This cement is like that. And I add this ultrafine calcium carbonate in addition to wake up the binder. The next model formulation is the self-leveling mortar. In this case, what we do, we start with the following hypothesis. We have 40% of powders. In these 40% of powders, we have 80% of cement and 12% of calcium carbonate, a GCC. I need to move, sorry. And in this case, the GCC is a ground calcium carbonate of high purity, but it is a normal one. You spoke about limestone. You can put this product in the limestone box. But in this case, this GCC has a calcium carbonate content of 99%, a methylene blue value of 0.3 gram per kilogram, and a surface area of 490 square meters per kilogram. The concentration of this calcium carbonate in this system is just to optimize the total powder content and achieve the best resistance to segregation. The water-cement ratio is 0.55, and the concentration of cement is just defined to reach 30 megapascal MPa at 28 days. This is the hypothesis. In this system, we decide to add the calcined clay, and we will add this calcined clay, that is to say, we will increase the total powder content, but we want to keep the same flow behavior. And in this case, we will not add more water, we will add more superplasticizer. The flow target is here, and we will use this mini Abrams cone. It is a normal Abrams cone divided by 2. And we are able to evaluate the flow, the viscosity with the wave funnel, and we are able also to prepare these mortars. This is in our lab in my team in Switzerland. This is for the mechanism. The protocol, the method is like that. Let's see the result and what we can see. We can see again that on this figure on the left, the proportion of calcined clay, by weight, of course. We don't speak about volume, because when we speak about cement, we don't speak about volume of something. We think about mass. So here we have the proportion of calcined clay, and here you have the necessary amount of superplasticizer to reach the same flow behavior. And what we can see again, that this one, the finer one, require more superplasticizer. In the meantime, we can do the parallel with the concentration of calcined clay and the compressive strength at 28 days. And we can see that for all of them, we have this positive contribution to the compressive strength, but they are different. We can also make this remark that this one, M4 here, is coarser, but it requires a lot of more superplasticizers than the other, and it has a positive contribution to the strength. It's just an information that D50 is interesting. It is a good indicator, but sometimes we can underestimate the real surface of such laminar products. The next step here is to show, perfect, the strength development of the system, but instead of addition of 4% of SCM, calcined clay, we have added 4% of cement. What we can see? We can see the quality of the cement. The compatibility cement superplasticizer is perfect. This cement, used as an extra component, in the recipe require less superplasticizers than the other. But in the meantime, when we go here on the figure on the right, we can see here the added value of this increase of cement concentration. We perform the system in terms of compressive strength, but we can see that some of these calcined clays have higher performance. This is just here the illustration that we have a huge interest to combine minerals, but in this way, to optimize the packing of the system, the stability, the flow, and so on. So we open the door to another discussion. We want to complete the view of the compressive strength and porosity with flowability and compatibility with superplasticizer. This is exactly where we are going to. The next step here is the data exploitation. Of course, with this sum of data, at the end of the day, we need to show some correlations, and it's clear and expected by all of us that at the end of the day, the calculation, forget the equation, but the calculation of the reactivity factor and the porosity allow us to show the linear correlation between porosity and strength. But what is important is not that. The key point is just to show that depending on the calcined clay selected in this system, higher is the fineness of the calcined clay, higher is the contribution to the strength. The second point, and really important point, is we need to introduce the question of flowability and compatibility with superplasticizer. Because the engineer knows the compatibility cement superplasticizer, but the compatibility superplasticizer SCM is totally unknown or not declared by the user, because the engineer has to play with after. Allez, Pascal. Next step. When we reach the point of conclusion, I have three main messages. The first one is the selection of mineral additions, such as calcined clay and others, and ground calcium carbonate, can be done with the keys of segmentation we have shown here, but it's not enough, definitely. And we need to consider the flow behavior, because compressive strength is important, but it's not enough. The second point concerning the superprecizer is we have seen that we need to speak about the concentration of the superprecizer and also the viscosity. I have in the lab that I manage sometimes the target of flow, but I have an issue on the viscosity. And the other point on that is really to speak about the added value of such calcium carbonate. I don't speak about limestone. We can speak about ground limestone because this is the standard we do, Richard. But it is a limestone of high purity with different fineness. That is to say, the engineer, oh, at school, we can select a GCC, a fine GCC, or an ultra-fine GCC produced by your companies. And this is the added value of our products. Finally, you remember the figures with the development of strength versus the concentration of water to cement ratio. Even if it seems to be simple, we can only, with this figure, try to find which combination can be used to reach 20 MPa or 8 MPa. So this set of model formulation is just a proposition to be able to consider the mineral addition in a new way and to prepare the combination that will be done by the engineer in the concrete lab and after on site. But definitely keep in mind that in some part of this world, we use ultra-fine calcium carbonate to solve some winter strength development issues. And I saw during we gave a presentation, Bill, in London 2024. And when I see the list of what can I do to wake up my system, ultra-fine calcium carbonate is not described, is not proposed. And we can do that. Dear Chairman, dear Nina, sorry for my French accent, but I was very happy to share this model formulation with you. And why? Because we produce calcium carbonate. And we don't learn calcium carbonate at school. We will be the first to have this ground limestone standard at the European level. But it's not enough. So please, when you make any paper or whatever, use a minima the key of segmentation, ground calcium carbonate, methylene blue value, and fineness. And then we will be able to explain the differences between a limestone and a ground calcium carbonate. We are not in competition, but we are different and we can be used in a different way. Thank you.
Pascal, over
cool.
you we can rely on a French person for a good formula on the screen. So,
cool.
We have time for one question, even if that's okay with you.
Sure.
Is there a question from the audience for Pascal? Yes, Mr.
Fantastic presentation, so thank you for that.
Merci.
I'm assuming you didn't extend this to concrete, it was just for mortars.
Yeah.
How do you anticipate going with particle packing?
Yeah.
And optimizing particle packing? I'm genuinely interested. From standardized sand, which you're using in your mortars, to real-world concretes, which use aggregates up to 20 mil. How do you optimize that and keep it optimized over a 12-month period?
I enjoyed this question because we're in 2024 and we started in 1993 to create the first concrete lab. And 1993 we started from scratch. We had the limestone at the plant and we have to sell it. Today the story is different. And I gave you this example from Bulgaria. We have a project with a cement company in Bulgaria and they have some ready-mix plant. And what do we see? They want to switch from a CM152 to a CM2ALL42. Since the beginning it's not easy. Huh? And they want to switch from 2 sand to 1 sand and a crushed sand. So what do? We have a tool like that to benchmark the sand and to see the water requirement, blah, blah, blah. We cut the formulation at the coarse aggregate, and we only focus on the mortar part. The concrete is a S3 consistence concrete. So when you do that, what do you obtain? Well, you obtain that. Allez, Pascal? Sorry? You obtain that. So when you are here, it's so easy. We are able to, because I use the mixing, the total content, water content given by the customer. I use this component. And with this micro concrete tool, I can play on the calcium carbonate content. And this is really the first things we do. Because you have a lot of concrete producers. You decide which cement. You decide the water to cement ratio with your experience. You decide which superprice sizer. And you don't know what is the optimum dosage of the calcium carbonate part. And what we do every time, and this is my daily work, and I will deal with that, keeping constant water to cement ratio and superprice sizer content, we play with the concentration of calcium carbonate and sand. Because when you do that, and that's why I gave you this figure here, when you do that, we do that. That is to say there is a point of saturation of the ground calcium carbonate. When you play on the concentration of the calcium carbonate, GCC, you will optimize the flow, you will reach a point, and you will decrease the flow. We did a paper with a political school from Lausanne. In the first part, this is a water paste. This is a paste thickness effect. It's not rocket science. And after, this is the issue of the water film thickness, because you have too much powder and not enough water. So this is what we do. We optimize first the packing and the stability of the system with the GCC. Second step, where is the need of the customer? If we want to increase the strength, he can play with the superprice sizer. If he says, it has sugar in tea, we are in London, not too much, or milk bill, not enough, I have enough superprice sizer. Do you want to add more cement? No? So what can we do? We can propose some fine GCC to optimize the fine packing. And what do we do? Again, the curve. If I add this fine GCC in the system, I must fill some voids. And this is what we saw for ultrafine GCC. We have added this ultrafine GCC in addition to the cement, and you saw the stability of the water requirement. Of course, if I add too much calcium carbonate of high fineness, I will need to add too much. I will need to add more superprice sizer and more water. And here, this is a mistake. Stop, we have enough. So this is what we do with our customer. During many years, coming from the Dollar School, it was a model, you remember, Swiss fair model, blah, blah, blah. But when we are with a concrete customer, we don't want to speak about a model formulation. I just tell him, we use your recipe because this is what you have success with that. Forget the coarse aggregate. We focus on the mortar part.
Thank you.
It's cool?
Appreciate it, yes.
Cool? It's simple, huh? But we have no other way to show the added value of our product.
Even the